So, Your Holiness, welcome to the second day of our dialogue, and thank you for agreeing to give us more of your time. I should say, by way of introduction, that again I am standing in for Anne Harrington. You should assume I am her. But also I am performing another function. Yesterday, Your Holiness, there were some unfortunate remarks between Arthur and Richie about the relationship between physics and neuroscience. There was the hint of competition between them. And we do not wish this to go further. So
we never thought that. I think that's the Western mentality.
So I should anyway explain that yesterday I was speaking a little about the history of the brain sciences. Today I'm chairing a session on quantum mechanics, about which I know very little. So perhaps this will help to seal the bridge between these two fields. Before we begin, I've been asked to make one or two announcements for the benefit of the whole gathering. The first one is that we, as everyone knows, are trying to facilitate a meeting between nuns who are present here and the women members of the Mind and Life team. It has not been possible to arrange these meetings on a regular basis at lunchtime, as we had said yesterday. So instead, we are going back to the original plan, which means that on the fourth day, in the evening at 7:30 p.m., there will be a meeting here for any nuns. Oh, in Losling, I'm sorry, not here. In Losling, the other bigger place, there will be a meeting of any nuns and any and all of the women members of the Mind and Life team. In fact, any women who are involved in this entire meeting who would like to meet together to speak about issues of mutual interest, please go to Losling at 7:30 in the evening on day 4. The other announcement I want to make is that in order to accommodate His Holiness's schedule, we have made a further adjustment to the plan for day 6, and that day will now begin at 7:30 in the morning and finish at 9:30 in the morning. So please make a note of that for the final day of the program.
Main reason, some problem in Bombay.
Yes.
So, say, I would like to reach Bombay that night. So the next day, the whole day.
Yes. Thank you. Thank you. That's no problem. We will have a bright and early start. So without further ado, I want to just make a short remark about this subject that we will spend this morning and this afternoon discussing. It is a subject, quantum mechanics, which has been present in the Mind and Life dialogues, I think, from the very beginning. And I know, Your Holiness, you have been particularly interested in this area of science for many years and have had the benefit of speaking to quite a number of physicists about this. Today we have two colleagues who are going to be particularly involved in the first session, and they will join us again with Thupten Jinpa in the afternoon session. I do want to just observe this is, especially for those like me who are not physicists, this is a tough area of modern science. There is a famous remark by the Nobel Prize-winning physicist Richard Feynman, who was an authority in this field during his lifetime, who once said, anyone who says they understand quantum mechanics does not understand quantum mechanics. So I say this to encourage those of us who find it challenging, and maybe that is all of us, that we should not expect this to be easy. On the other hand, we know that it is of interest and that it is of fundamental interest. So perhaps with that cautionary note, I'll turn to our first speaker, known well to us all, Arthur Zients, who will lead us through this field.
Thank you very much, John. Good morning, Your Holiness. Your introduction puts me in a very awkward position. Because if I say I understand quantum mechanics, then clearly I don't understand quantum mechanics. And if I don't understand quantum mechanics, why am I here?
Sorry.
Quite logical.
Yes. All right. The implications of quantum mechanics for our view of reality, that's really the topic we have before us. You know, yesterday, we spent some time talking about our understanding and view of reality in a more conventional, classical sense in the world of physics. Galileo, looking through his telescope, making careful observations, reasoning from those observations to inferences based on his observations and logic. We have done an enormous amount of good work in that regard. But about 120 years ago, physicists who had really worked hard using observation, experimentation, and logic, reasoning, felt that they had come essentially to the end of their subject. I'm going to show just a picture of that community. We tend to think of this community of physicists as must be thousands and thousands of them. And of course now that's true. But in the time of around 1900 to 1927, when this photograph was taken, when the birth of quantum physics took place, it was a relative handful of people who were thinking the new thoughts, the new physics. And there were, according to one of them, an English physicist by the name of Lord Kelvin, he said, really, we understand everything except two small clouds on the horizon. So the sky was perfectly blue, except for these two small clouds. The one was what I call the color of candlelight. When you light a candle, you see the flame, and the flame has got a particular color. And you can ask yourself, why does it have that color? Now, in the classical physics, you would bring all of your careful understandings of heat, of light, and so forth to this subject. The simple question, light a candle, why is it the color it is? It turns out you can't properly explain that color. You can make measurements, you can pass light through the prism and see its colors, but the distribution of colors, the color of the candlelight, you can't predict. So Lord Kelvin said, this is a problem. Why can't we predict the simple phenomenon of candlelight? The second one is more complicated. You know, yesterday we were talking about sound on the moon and the fact that you needed air in order for sound to propagate. If you take the air out of this room, well, we all would die, but in the middle of that process we would be yelling at each other and we would hear nothing, right? Because there was no air to carry the sound. But if you think about it for a minute, it's also remarkable that on the moon there's no air, but I can see the other astronaut. So I'm taking a photograph, and the light passes through a space with no air. The sound cannot pass through the space, but light can pass through space with no air. So in 1900, physicists asked, well, there must be something still, even without any air. Exactly, because light was considered a wave, just like sound. There must be something waving. Up here you see water, and you can see little waves on the water. Or you can have... it needs to be a medium, a thing, something like air that is waving. That's the logic, yeah? And maybe it's a big wave, like this one. Yeah. But the concept of a wave of sound, a wave of light, seems so logical that when people looked for the medium, the ether it was called, that would carry the light wave, they felt sure they must find it. But they never found it. Even to this day, it's never been found. And so we now believe there is no ether. There is no light-carrying medium. All right? So this is the second experiment that was done. So there are two key experiments. One, an experiment trying to study and understand the color of candlelight. The second, what's the medium that carries light? In order to solve these questions, two new theories were developed. The first is quantum physics, that was connected with the color of candlelight. The second is the theory of Einstein's relativity. When you take the assumptions and calculations of the new physics of quantum mechanics, the color of candlelight can be predicted perfectly. When you understand Einstein's relativity and apply it to space and time, you realize there is no need for a medium called the luminiferous ether. The ether, light can travel without. So that is the birth, you could say, from these two small clouds of two huge theories which change fundamentally change our picture of reality. Now, quantum mechanics is, as Feynman and many have said, very difficult to understand. Its ideas are very counterintuitive, and there are various ways to approach the understanding of quantum mechanics. I will introduce one concept. Michelle Bitbol, my friend and colleague, will introduce others, and gradually we'll build up the key elements of what's necessary to understand this new concepts, these new ideas, and their implications, both philosophical and practical. So we'll look at the question of the principles of quantum mechanics. I'll pick just the one which is already very challenging. I have here two coins. I've put a couple of coins up on the screen so everyone can see. But I have here two coins, two, in my case, 5 rupee coins. Up there are 10 rupees. The question is, well, it's a kind of a stupid question. How do you know there are two? Well, you can tell them apart because they're located in different places. There's one on the right, there's one on the left. Also, this one has a little scratch. It's a little different than this one. They're very similar, but they're not exactly the same. If I try to put them in the same place, I can't put them in the same place. They can't occupy the same volume. But what if the two entities are not coins, but atoms or electrons or what have you? Now, in that case, you have a very different situation. The two atoms, whatever atom A and atom B may be, they are absolutely identical. There's no scratch on one. There's nothing that would tell you this is atom A or this is atom B. They're completely twins. Yeah? But you can say, yes, but still one is on the left and the other is on the right. But in quantum physics, you have a situation where these two, which are separated, can actually overlap. Yes, just leave it. You leave the slide up. This is a new slide. Okay. Yeah.
Say, for example, the analogy of the two coins.
I think generally, it's atom level, small particle is always moving. So not necessarily the same direction. One atom go this way, or one another way. So two coins, the same nature, because of the combust, it is a very subtle sort of particles. But each atom is a different way of moving.
Right.
So not exact.
Yeah.
Same.
Well, it turns out that if you have, let's say, a hydrogen atom and a hydrogen atom, two very simple atoms, there is nothing by which you can distinguish them. They're exactly twins.
But what about their movement, the spin directions? Are they all exactly the same?
Yes. Let's just say yes. I mean,
yes.
Well, the problem is you're using a classical concept, namely that there's a movement of an electron in a particular trajectory, like you have in these pictures here. This is really a wrong image. You can't imagine. The electron itself has no specific location, and it has no specific trajectory, no path by which it moves. All right? So you have the picture which most people have, that the atom is like a planetary system with planets moving around the sun. That's an approximation, but it turns out to be wrong. The key thing is that they're indistinguishable. Atom A and atom B are exactly the same.
The same location, exactly the same location of the one.
Atom, yes, the atom of hydrogen.
So what about the location? Can we say exactly?
Now classically, you can't overlap two objects. These two coins cannot. But the two atoms can not only overlap, but can occupy the same place.
아니 저는 수제 말와.
말다디 더 구두잖아 지난전다 클래시컬 그 삼당나 제베는 수진 공도요 말이야. 때네 단다 뭐감르고 사베 돈에 게 셰베나 더 수진 공고 샤단 거라. 가가지 제 인지미지 수진나 간다 거기서 지
단도 열어 톡바드 자와. 자 톡바 매봐. 다 톡바 매버 리범고 샤 패샤도 그래.
그 간다 유코섬는 뭐죠? 고르바다 지난전에 수진 다 구주 인지미지베 간다 dü니 유코서 찍가 내도 그랬어.
I think you have to have a different concept of the atom. The atom is not solid in the way in which we normally think. If I think of the warmth of my body,
그냥 that moves 잖아요. 다 relatively forward
So the moment we use the notion of movement, then whatever may be the framework, within that framework we can talk about relative direction.
So one might be moving one way, one might be moving the other way.
Yeah.
So
in that case, there's anything that has a direction, even though it may be relative, we can speak about its front and back.
Yes, but in quantum mechanics, everything depends on, you could say, not only these principles of identity, but also of observation. Right? If you observe a particular atom, then it becomes a kind of object. All right? But if you don't observe, then there's an ambiguity, a lack of knowledge. Right? Now, normally, in physics or in realities, if you don't observe something, it doesn't matter, right? These two objects are separated, whether I look at them or not. So when you say something is moving, you're presupposing you're observing.
Quantum level kan lebe na ane jeje lo da.
독식 동하면 다 매배
다 매배 소리 kan lewer. 다 tikinge ma kamme choson ta dikan to besere. Ta inda kurang songdan chige na quantum ka kan lebe ka be ya ane suchen kurang ko ngo sam dang da sabas ta na ma to nge ma ta classical ki ngukam ri ba de kiyong be na ane kendu mangbo shibuji.
Okay, so
am I right in explaining to His Holiness the point you are making is that when we think at the quantum level, if we bring in the notions and concepts from the classical physics, then we run into all these contradictions.
Right, exactly.
So we need to have a whole new way of thinking.
You have to have a whole new, and I think it's best to go stepwise. So the first is that each of the atoms, say hydrogen atom and one and hydrogen atom two, they're duplicates. They're exactly the same, not like a coin, and they also can interpenetrate. They can overlap, or they can occupy the same volume. These are not possible in classical physics or in normal life, right? Unless, of course, you have special powers. So.
But then, but given that the quantum mechanics is still called physics, you're supposedly talking about physical reality, aren't you?
Yes, but at a very subtle level.
But one can progressively go subtler and subtler.
Yes,
but are you suggesting there's a disjunction?
That's one of the great challenges of quantum physics, right there. How do you go from what is true at the microscopic level? And we know that quantum mechanics is true when you have billions of atoms. We've done measurements that show that that is true. But when does it become like this world, which is so different in its laws and principles? And this is one of the great questions that still exists within quantum physics. And there are arguments, disputes, as to how to understand that transition. So, I'm going to take us one step further. This concept is called indistinguishability. I don't know, is that a concept in?
Okay.
So atom A or atom B are indistinguishable, or the picture of Your Holiness on the right is indistinguishable from the picture of Your Holiness on the left. Now, I'm going to allow for these two images to overlap, just like the atom. All right, so we can bring them together. Now I'm going to allow them to come apart, but there's an ambiguity, because they could come apart this way, or they could come apart this way, right? So they could come apart like this, and you're not sure whether when they came together, they continued, or they went back. Logic, okay? It's only thinking, but it has huge implications. So there are two options. Here's A and B, and then we bring A and B together, and we can go back to A and B as they were in the beginning, or I can end with B on the left and A on the right. Now I have B, A. So, right, you go like this, or I can go like this. Now,
Holiness is wondering to what extent actually those kind of distinctions are purely at the conceptual level, or actually at the objective physical level of reality.
Yes, right. Well, let's stand up and do our little demonstration. We have a demonstration.
Experiment.
Now, what's important in quantum mechanics is that the two objects John and I are dressed almost alike, right?
Sorry.
So, but we're going to interact. I can't get inside of him, but we interact, we hit each other. And there are two options. You go back and sit down in your chair. That's one option. The other is that we bump shoulders, we pass by each other, and we sit down.
다들 추니 투두가라 다그 투베 슈굴이야 초카원 도마들 다 담칸이여 봐. 예.
Okay.
I think that's most difficult part to understand. Yeah,
That's
Still,
easy.
His Holiness is trying to figure out what you are getting at.
You're very patient. Okay. What I'm getting at is the following. What allowed you to make this seem so obvious is that you were watching two grown men, right, acting very silly. And it seemed like you could follow which was going where. Yeah? But now in quantum mechanics, when you have this principle of indistinguishability, the first option and the second option are not distinguishable from one another. It's hidden. When you look at the end and you see John in this chair or me in this chair, then the hidden character disappears. But in the quantum mechanical phase, in the quantum mechanics of this, that is hidden. And when it's hidden from view, then a new possibility arises.
수진 라베 가서 저와디 뒤처로 간 루즈는 저와디 샤도 몰라. 다 말해.
말에 쿠란 데르시탄데 다 드테니 뒤처럼니 투베나 다 투베 슈굴이야 초카원도 만도데.
들어.
군이 니가 지부지장 인자 초카원도 만도데 임제당 두고요 말했어. 동오벌이야 투베 슈굴이 예 직이열도 직연도 야 야는 디 연구를 봤어. 때는디 다나 수전 라벤 내가블이야 뭐통
들어.
타면 내가블은 quantum level이야 다토고요 말했어.
So when it's hidden, then we have a new concept which is called superposition. That you take this and you add it to that, right? You take both possibilities, even though they are logically distinct, and you put them together in a new kind of relationship, a new state of matter, which is not to be understood classically. This is the part which Einstein complained of, and which Feynman said, if you think you understand this, you don't understand this. Because it's a new concept, a concept where it's neither one or the other, but in some sense both, right? So what you have then is when Your Holiness comes together and then they're separated, you actually have to add option 1, which is A on the left, B on the right, with option 2, which is B on the left and A on the right. This is called a coherent superposition state. Now, you'd say, how do you know this is true? Why should this make any difference? Is this just physicists thinking logically and spinning out theories, or is this fact? Is this true? And is it important? I give you just 2 examples to begin with, or maybe 3. Chemistry requires this ambiguity. You know, and hydrogen does not occur as a hydrogen atom alone, it always occurs as a hydrogen molecule, H2. If you ask what's the force that holds them together, it's the force that arises from this so-called ambiguity, this quantum superposition state. That's the covalent bond. So you could say everything around us holds together because of this quantum mechanical confusion. It's not confusion for nature, but for us and our normal logic, this is so powerful that it organizes all of the substances around us. It also creates something we now call quantum holism. I understand there's this concept of Indra's net, where in every place there is an image of every other place. So it's as if there's a jewel. It's as if there's a jewel and it mirrors every other jewel in a net, so that you look into one object but you see all objects. When John and I bumped shoulders, we became what's called entangled. We became connected. And then if you and I bump shoulders, another part of the net is created, and John and I both now become entangled with you. And you and I and John are all now part of this relationship, and then with Jimpa and everyone in the room, right? So you start with a single atom, you connect it to one, it interacts, now it's entangled, and you create this holistic set of relationships, as long as its indistinguishability is still held. So you gradually propagate this, and this kind of holism is now being used for technological purposes. In other words, in the United States, we're very practical. And so the physicists are doing their thinking, and where most people are not interested. What difference does it make? But now that we can create computers built on this concept, if this concept were false, then these computers would not operate. If this concept is true, then they can operate. And they can, for certain kinds of problems, calculational problems, very important calculation problems, they can work extremely fast. You know, when you swipe your credit card and it says a secure transaction, it codes your transaction into a secret kind of mathematical expression, sends it, and then it's decoded. And it would take many, many centuries, perhaps even billions of years, to decode that transaction. Such computers, though, have the promise of doing this instantly, essentially instantly, in a matter of seconds. They're very powerful because they have the holism as part of their computational power, not individuals calculating, but it's as if all of the people in this room, all of their intelligence was reflected holistically into the computer itself.
이민 가능 세저바 대중은 임바다 마임바니 부디 뭔게 마도 되니만도 들어서요 말봐 다 quantum superposition 게 시베갈 이민 가능 세저 풍순변 내가 부디 샤고니시 다 풍순변 내가 부디 안 가르슬는 편준 제외 되변 제와 요변도 제외 땡네 샤운디가라 아니 superpositions.
Yeah.
Am I right in understanding this to be some kind of the middle, which defies the law of excluded middle? It's neither A nor B, somewhere in the middle. It's almost like both or...
It's a little more complicated than that still, I'm afraid, but let's say yes for the moment.
For the moment, yeah.
For the moment. I think in this case, the important thing is to think, let's say you want to do an addition or a calculation that's very difficult. If you do it alone, it may take you a long time. If you can break up the calculation into parts and give Jimpa something to do, Christoph something to do, Richie, and each of the people in this room part of the calculation, it'll go much faster because you've divided it up. Now imagine the possibility that all of their intelligences can be put on you. That you enfold, you take all of their capacities and you have that in one place, not distributed amongst many individuals. That's normal parallel computing. But in quantum computation, all of those quantum objects in the world now can be superposed in one quantum register, in one quantum place. So you have one quantum individual with the intelligence of many, you could say. And then when that computation runs, it runs quantum mechanically with all of these entanglements and can provide the answer very quickly. All right? So that's a totally new possibility, and it has been demonstrated to be the case. Anton Zeilinger, who you know in Austria, the physicist, is...
Right.
In Wien, in Vienna, and prior when we were in Innsbruck together, Anton with the beard and all the hair. Remember him? Yeah. So he's an expert in this field.
He's the one who demonstrated what was it? What is it
Wave
called?
particle duality.
Double slit
experiment. Yes, that's the one, Your Holiness. He had a piece of equipment here. Yes, same person. He's the world expert.
Indeterminacy. Randomness. Random.
Random or random shapes.
Yeah, he talked about randomness.
Yes, because one of the fundamental characteristics of quantum mechanics is what we call objective randomness, that certain events take place without a cause, which you found also challenging at the time. Yes? I think this concept of superposition is so important and so difficult to understand that I'm going to demonstrate it with these four women here. It's the same woman with 4 hair colors. Now, normally, you have to have one hair color or the other, unless, of course, you have no hair. Then you have the potential for hair color.
Oh, yes. But at least, you see, you can make different color.
Yeah.
We still have some.
Mine has gotten a little long, I know. Yeah. But here you have 4 different hair colors on 4 different women. Well, actually, on the same woman.
Right.
In superposition, you can have all 4 at the same time. So it's as if all 4 of these women came to one place. And of course, color in the physics standpoint is talked about as a wave, and of a certain wavelength is one way of speaking about color. So the question is, can you create the most elementary form of light with 4 hair colors, for example? So can a photon, which is the single smallest unit of energy of light, is it one color? Or can it be 2 colors? Or 3 colors? Or 4 colors? And the answer is, experiments that I and others have done show that yes, it can be 2 colors or more. So we tend to think that the properties of things... So a single quantum of light can be emitted with 2 different colors. Or a single quantum of light can go in...
So the source of the light and then the light itself, aren't they composed of the same material?
The source of the light is an atom, which has substance, it has mass.
The light itself also is
light itself has no mass, no rest mass.
the dio mar karsan jitse yo marwa öyle ya tan rö yongse shidi sujen atom duran che da tele jitse ji yo che to ö koran ya
안 도저해서.
la
안 도저해서.
to toje
지야 도저.
the atom did toje chagorwa. So in that case the source of light atom is still in almost in classical terms it's an obstructive. It has a spatially obstructive property.
Has a spatially obstructive property, yes. So you can collide those atoms, you're right? Whereas light can pass through.
Light can pass through.
Yeah.
자상 뒤니 못 찍도 돼도.
So how does that?
냠돌이야. 실도 참모 인자. 냠도도 도로토로. 맞으로 라고 뭐라. 야단 제베서 통그레디 뭐도랑 나당이야. 그니 지시 고서 사대에 있는 제도 말아.
So in that case, if they can collide, and if each of these atoms have spatially obstructive property, because they're so subtle, it may seem as if they're occupying the same space. Can it still be the case that they are?
How can they possibly occupy the same
space?
Yeah. Here's the way we now think of these particles. Take the simplest particle, the electron. Right? It has a very, very small mass. It has what we call charge, which allows a force to act between electrons, so there's a force. But if you ask what's its size, how big is it, now our best view is that it has no size. In other words, there's a kind of location around which there's a center of force, given by this by the mass and the electrical and magnetic properties, so that there is a force field. Take a second electron and you bring it close, the forces between them will cause them to deflect, but they can overlap, and with high enough energies they can overlap essentially completely. So you have So you don't have a hard surface like this.
Electron force So in other words, to use a plain English, it's got no shape.
Under certain circumstances, atoms do have shapes, but it's they're structures which are what would you call it? They're gentle structures. They're not fixed. They're not hard structures. More like clouds. Or think of the body has warmth, and near me, outside of me, there's also warmth, right? So there's a warmth shape, but it's not obstructive, right? When you come closer, then you hit the skin, the flesh, and it becomes obstructive. So the atoms are more like the energy bodies or the warmth body around me. So you have two types of particles in fundamental physics. You have those which are like the electrons and which are more solid and which have obstruction, and those which are like the photon, which are purely able to pass through one another. There's no obstruction at all. Okay, let me go on. The other strange, another strange property is that these particles can go two ways at the same time. Right? When you come to a path which has a fork in the road, then you either go to the right or you go to the left. But a single quantum, a single photon, for example, or a single electron, can be sent. If you see on the left-hand side, you see there's a blue dot, and that blue dot can go both ways. So the single object doesn't split in half. That's a hard thing, again, to understand, but it goes into, again, a superposition state. It's as if the Dalai...
도서
도부셔 매서.
도부체메스 근데 도서 초니갈 두겨래서
뒤지래.
no at one simultaneously.
Simultaneously, it goes into a new kind of state. Right? You shouldn't really think of it following a real trajectory, but you should think of it goes into a new state which is ambiguous,
This
but which corresponds to both possibilities.
가봐도 매번 사람 더 두고 봐.
나래 말다
그 뒤질이야. 니 집에 있네.
나래다 코란 게
참이 직.
나래
니 그래서 그래.
근데 코란 비디스 그래서 내가 코란 수진게 내가 브랜드 나란도 수진지 대 내가 마샤 버차지 딱 간다 강롱 세저와 딘 내가 중문지 제배는 이간도 줘. So his Holiness is saying that how can this single atom I mean one can talk about
참이.
So this is basically a simple indivisible
Indivisible,
part.
right,
Yeah.
quantum.
So so it's one thing to say that you can talk about indeterminate
Yeah, exactly.
path. So
Right.
that state can be understood.
Yes.
But how can then make the jump and say that it actually goes through both?
Yeah, right.
야, 참이죠 더 살아.
Because
What's the evidence?
because when we always said that it's a simple indivisible. So
Yes.
it's not splitting into two.
Right. So if you have, there are experiments. If you set up this experiment, as I've done,
다양 간일 집어도 쉬고 직수 투투 말해.
So what about that it goes into both parts, but then
A moment become two. Now again you see become one.
do they collapse into one? Can one conceive the possibility that it goes in through the both parts by splitting
Okay.
and then collapse?
So
back?
this is the wave-particle duality. This is what Anton was showing you, all right, when you were doing the experiment on the desk. If you take that single indivisible particle and you put it into this, what we call beam splitter, you put it into a divider and two paths, you could say, well, maybe it goes one way or maybe it goes the other way. Yeah, half the time it goes to the right, half the time it goes straight ahead. Yeah? And then you measure, and if you measure and ask that question, then you in fact always find it goes one way or the other way. But if you don't ask the question which way, and you leave that ambiguous
지들이.
and bring them back together, then you see a phenomenon which can only be understood by it going both ways, namely a wave-like interference effect. So
강도
this,
그런 게 매번 때 인거 봐.
나는 구주단 때 욕서 그러자. The experiment 제사be 주고대 가완의 침부 때베나 더 두랑 뭐지 때베나 아니 experiment 제사be 주고대 초간의 침마진데 네바 가다 찍모도 좀 해봐체. 다 이내 구둘랍 그런 신체 이게 시고로 뒤디기디. 디전 때베나 아니 그 데이터 같은 테이블 따인데 걸라 디 초니가네 침버서 말았나 대체 제매 대체 제마토니 된대기네 주는 거래서 딘산다
아도 참면도 되게 네 가서 partless라. Partless. That very subtle.
very
It also
subtle.
momentarily changing.
Pardon me?
It also momentarily changing.
is it also in
Changing
motion
from, yes, it's in motion. Yes, but the direction is ambiguous. But it's ambiguous again in a different way. If I take two coins, and one is a 5 rupee coin and one is a 1 rupee coin, if you close your eyes for a minute, and I give you one of the coins,
I mean,
no, look, don't look. No cheating. And you don't look, then you don't know which coin is in your hand. If you look, you can look at your coin, Your Holiness.
누구도 없다는 말해.
but can't you
Oh,
just
you
feel it
You're looking with your fingers. Okay, but what coin do you have?
Or maybe
Smell.
some distinction.
Some distinction. What coin do you have?
가기는 고문가 들으셔 5 rupee
Yes.
So 5 rupee coin? Well, if there was a 5 rupee coin and a 1 rupee coin, then which one do I have? I have the 1 rupee coin. It's logic, right? So in the quantum mechanical case, as long as you do not look, there's this ambiguity. In classical physics, it's always the case that there really is a 5 rupee coin here and a 1 rupee coin there. But it could be like with John, you could have the 1 rupee coin and I could have the 5 rupee coin. In quantum mechanics, that ambiguity becomes a powerful reality. It actually is not just ignorance, right? But is actually a positive state, a superposition state. Right?
그때 낭배한다. 저시 되어야래. 가서 도지기 더 랑징 똑바 뒤에나 뒤에봐. 랑징 똑바 매나 매봐. 그래서 자식 그래서 깨셔야 된다.
된대나?
당연히 그랬어.
Yes.
삼삼배.
No.
더 치료 가야 돼.
No. So
Again, indistinguishability.
I think you also studied that. So should be no problem. The mind-only school of thought.
Yes.
So long, the kasa, the 징행 똑같이 뭐 디어레스. 똑같으면 디어 말이지. 근데 인도산에 그 진지 똑같이 안에 그 박자 써도 샤르마도 그게 질던 거 말이죠.
So, in fact, in the Buddhist philosophical world, because of these kind of issues of the actual what constitutes the existence of something,
yes,
there was a mind-only school felt the need to really eventually conclude that ultimately it is determined on the basis of whether or
only
not
mind.
there is a cognition of it. And if there is a cognition of it, then it exists. And if there is no cognition of it, it doesn't exist.
Yes, and there are very famous physicists like Eugene Wigner who said exactly the same thing. That somehow the ambiguity exists as long as you do not look and cognize 5 rupees, then you must have 1 rupee. Yeah? So that my cognition also can have an effect on what your subsequent cognition must be. Right? It has to be consistent. There has to be a consistency among the cognitions.
There is then the nujobe quantum theory banalole then simsa manashi. Then chungbares. Then the chitan shitan cheba na quantum ki ngokam rebatone shebe na ngimege nekapti yobazinya the catching bush zigores. Ngimege di ko chitan nganju matong wainza ngeba meba tesam masha bachache.
Yeah, and the important thing to realize is as long as you do not look, then there are new phenomena that are possible. As long as you do not look to see if it's 5 and 1 or 1 and 5, right? Then there's this superposition or entangled state. There's this connectedness that has reality, that has consequences, that has new machines, that has new kinds of computers and so forth. New kinds of secret messages can be transmitted in quantum cryptography. There's a whole new field of quantum information theory, like in computer science. So these, what seem to be very philosophical points, actually have vast consequences. Yeah. Thank you for the rupee. I want to summarize what my main points were, right?
Interaction.
That you have a classical ambiguity, just ignorance, actually becomes something quite positive, becomes something we call quantum superposition. The 2 options, which in classical thinking you pick one or the other. Yeah. In classical physics, you pick one path or the other, one object or the other, but now you have the possibility of, if they're indistinguishable, of holding them both, and a new kind of reality, a new aspect of reality is manifest. It becomes then a powerful factor in nature. For example, all of chemistry depends upon this, and the new quantum technologies as well, so we can apply this into practical devices. Yeah? So this is not just something which is off in a corner somewhere that has no significance. You could say reality depends, physical reality, these things and our technologies really depend on these. Your cell phones, for example, wouldn't operate if you didn't have this. Tunnel diodes and the like. Okay, so there's also then somewhat hidden, we don't see this, but at a very subtle level, there's a hidden connectedness or entanglement, holism as we call it, quantum holism in nature, which indicates at a subtle level a certain kind of interconnectedness. Yeah? That things are apparently discrete, and at one level that's true, but at a more subtle level, they have an interconnections with one another.
So the quantum condition is the whole galaxies, but different galaxies. That
So one can, so from the quantum point of view, then one can even talk about this interconnected at the cosmos level between the galaxies.
Well, this is more speculation, right? But one can begin to think. Every particle that has interacted with another particle has a connection to that particle that propagates and goes further and further, branches. And so from a logical standpoint, it would make sense to think that many, many parts of the universe are connected. Now, in ways which are hard for us to imagine. But in these simple cases, we can actually do experiments which show the connectedness.
저는 레뷰 내고 다 디자로 가져올 다 듀처로 저러. 그 듀네고 찍버려.
나를 나
듀네고 찍버주고 왜.
기운기 전에 좀
그 맞다. 기운기 좀다. 그 듀처로 그랑 신저러.
나를
그 안에 레뷰 내고 줄 때가 다가나. 디 듀네고로 그 찍어 여서 그래서 말해. 그 듀디 듀처로 주십시오 저러다. 레뷰디 듀처로 주십시오.
So, for example, if you think of two, facts, one is a cause and one is an effect. So there is a temporal sequence, but the material. So we're talking about the material objects, material phenomena. So temporally there is a sequence, but at the constitutive level, would you say that the atoms that compose whatever the cause is exactly the same as the atoms that the material constituents of the effect?
So, in other words, the very concept of cause and effect on grosser level, very subtle level.
It's very more difficult there.
Then,
yeah, this is quite interesting.
On the Big Bang, cosmos 찾아서 the atoms
For example, yes, I can give an example where this time sequence, if you have certain kinds of particle interactions, let's just say that give off light, normally you would think classically they have to have the collision, then the light is given off. This is the cause, that's the effect. But if you assume that, you get the wrong calculation. If you assume that just a little bit early, just prior to the collision, there's an emission, and a little bit after the collision, there's emission, and you take both options, both possibilities, in this superposition, then you get the correct response, you get the correct prediction. In other words, cause and effect, time sequencing becomes ambiguous again, all right? So before and after ambiguity. So time ambiguities, spatial and direction ambiguities, energy ambiguities, they all can lead to this new quantum superposition and then quantum connections. But this is at a very subtle
the very sort of smallest particle level, one particle can multiply?
Well, one particle can multiply if there's energy. Yeah, so... okay.
It's a Big Bang.
It can't come from...
It's a tremendous sort of energy. Something to multiply.
So if you take two particles, and you collide them, you can get many particles. And it's even if the two particles are elementary. They're not divisible, like two electrons.
That multiply multiply 용서지다 multiply 되는 뭐지 말봐.
뭐지고 말해서
뭐지고 말봐.
라렘. So
뭐 다르신 서로.
라렘. So when two particles collide and you multiply, then where the multiplied particles are coming from
the
cannot be exactly the same as the source.
We say they come from the energy of the collision. This has to do with Einstein's understanding of mass-energy relation, right? That there's a certain amount of energy can be used to generate a massive particle, so that this could go back and forth. In a certain sense, mass is energy, but a very small amount of mass gives rise to a very huge amount of energy.
So in
that case, we can say that at the causal stage, there could be one or two atoms. So you have, say, two atoms. But at the resultant stage, there are many atoms.
There could be many.
There could be many atoms.
Yes, that's often in CERN. This is absolutely routine. You take two electrons or two protons and you crash them together very energetically. They collide, and then you get a huge number of particles, hundreds, thousands.
The collision chain go to multiply you naga kare.
Then the Quran shows the collide chebeke nube nishujorwa. Dine chumbres. Mato atom need pa tumbu chibeke jeremdu. So when the two atoms, say two particles collide and then multiply, so where are the multiplied particles coming from? They're not being split from the original two particles.
No, they're not being split. They're being generated. They're being born out of energy. Yeah. When you hit your hands together a number of times, they start to feel warm. Where does that come from? Where does that warmth come from?
The blood.
It comes from can in some ways be thought to come from the energy of hitting, right? And so you can take two particles and hit, and not only do they get warm, but they get so warm that they generate new particles from the, you could say, heat of the interaction, the energy of the interaction. Yeah, the energy of the collision. What's harder
So what is the
explanation?
The kind of the explanation for why at this intense heat generated, there is this multiplication happening?
Why is there this multiplication happening? Well,
is there kind of
there is
theory
a theory,
that
certainly there's a theory, quantum chromodynamics. I don't know whether I can go there even if I wanted to. It's a very, very complex theory, but basically it gives you the predictions of how many particles appear, how many subsequent particles decay. All of the details of the interaction are quite predictable now. This was the reason the Higgs boson discovery was so important. It completed the picture for what we now have as a quite unified picture of what we call the electromagnetic, the weak and the strong interactions. So those all come together. The new particles that are generated can be understood in terms of quarks and their interactions with gluons. I mean, it's a very elaborate picture, but it's powerful and very, very accurate and predictive. There's still quite a wide range of mysteries. Yes, I mean, we still have gravity has not been included in the global picture. It stays outside of this beautiful theory. Also, there are still 96% of the universe missing, you could say. So what's that made of, and how do we understand that? So there's still lots to learn. But there is a theory which can account for the production and branching ratios of the...
Thermodynamics ki rodang tone se she yores yobatum do masebe ani particle ni tonga jabe ka ya tonga jab chechung ki energy tone ani du saba ka ju ke ma ke ta ti gyurung do ka ju ne mane da ju sang ma 원순에 프로젝트도 그래서.
저 가서 공간다. 공말 왜?
네.
대 university로 전한다. dark
나름
cosmology가.
나름 dark matter.
좋아.
나름.
대다도 추적다 가도 즉 속진을 주denge지. 지가 알았다.
네.
근데 I don't talk 찍고 봐.
Right. So yesterday you spoke about the dark matter, and then we spoke about, in contrast to that, the known material
Known matter,
properties,
yeah.
known matter. So at the level of constitution, would you say they're made from the same?
Same.
At the particle level?
Actually, people think they're not. There are many speculations as to what they might be. I think right now there's something called the weakly interacting massive particles, which is a euphemism, which is just a way of saying that these particles must have mass because they look like they have mass in these galaxies, and they're very weakly interacting, which means we can't see them. So they're like invisible but massive particles. But we know they're not made of what we call baryonic matter, the kind of matter that's around the room here. Even antiparticles we know. But this is a new class, it's a new kind of substance. That's our best guess right now. So it's not the kind of matter, not even the type.
최바로 최비나 galaxies 가사디 가사지 우차래. 빅뱅.
맞아.
빅뱅 뭐중 공래. 다 자고 저러.
네.
나 안다 디가서 바 뭐를 찍을 자고 서러. 딘 잡아 가야.
네.
안다 가서 galaxy 차. 다 빅뱅 중산에.
네.
다 galaxy 먹고 차도 그러려야 나한테 대 가서
dark matter.
dark matter 저러.
네.
자 빅뱅 뭐중 dark matter 요구.
So
딘 잡아 가야.
So logically one would expect that before the Big Bang, maybe dark matter that you're talking about might have existed.
There might be.
Might be. I couldn't say.
Yes.
Yeah.
So, Your Holiness, I think we should give Arthur a rest.
Thank you.
But we won't
very
give
much.
you a rest.
Thank you.
Thank you very much.
Thank you. And we're going to suggest that Michel come and give his presentation on the same area of science, but from a slightly different angle.
Yes.
Yes.
This is called quantum superposition, the hug.
Okay, so I have to find.
Oh, okay.
So, what is the name of... Michel Bitpol comes to us from the CNRS in Paris, and he's going to put up his presentation.
Yes.
Michel, what is it called for the sake of the people running the...
It's so quantum mechanics. So it's Bitpol Morning.
Bitpol Morning is the name of this file that we need for the friends who are providing the Tibetan
Yes.
translation.
So, Your Holiness, it's a joy and honor to be here and speak to you about the philosophy of quantum mechanics, even though I'm sure it's a challenge for me because I know you know a lot about that. I've read your book, The Universe in a Single Atom. I know that you have met David Bohm, Anton Zeilinger, Carl Friedrich von Weizsäcker, and so you know a lot. But
Usually I describe the hopeless student of quantum
physics.
mechanics, quantum physics. I really seriously solicited lessons or explanation from late David Bohm,
yes,
few occasions. Then later, the von Weizsäcker, also is late von Weizsäcker.
yes, that's right.
See, during I listen quantum physics, it seems to say I understand something. After finishing, nothing left. So your description is
So what you said
that.
about the understanding or not understanding quantum physics was quite true.
Okay. So we all have challenges here.
Yeah.
I think is the main thing. All of us.
So I hope it will not be worse with me. I hope. So the challenge will be to dig into the philosophy of quantum mechanics and to understand something very important about the difference between classical and quantum physics. You know that classical physics could go
Michelle,
on.
can you take that little bit? Yeah, yeah.
Just pull it away from your mouth.
Yeah, that's good.
Classical physics could go on by supposing that bodies had an intrinsic existence, and some intrinsic properties such as mass or extension and so on. But in quantum physics, this idea that bodies have intrinsic existence and properties are intrinsically ascribed to the particles becomes a challenge. It becomes very difficult to sustain that at that point in quantum mechanics, even though certain physicists are still very eager to keep this old idea, this old absolutist idea of classical physics, they encounter so many difficulties that sometimes they renounce. So here I will insist on that, on the critique of the idea of intrinsic existence of bodies and of the idea that they have intrinsic properties. So to begin with, to illustrate this idea, I want to take a very simple example of how understanding of a certain situation can be improved largely by renouncing the idea of intrinsic properties. So my example comes from my own life. When I was a child, maybe I was 6, maybe I was 7 or 8, I don't remember, but I was riding a bicycle on the road in the night, and I was seeing the moon on my right, and also the line of trees. And a strange phenomenon occurred. When I was riding my bicycle, I saw that the moon was following me. And when I was stopping, I saw that the moon was stopping with me. And I was surprised. I thought, what's so special with me that the moon is following me? What's so special with the moon that it knows what I do? And so I was thinking about the intrinsic properties of the moon and of me that could explain that strange phenomenon. Then, when I was a little bit more grown up, when I was, say, 12 years old, I suddenly understood it had nothing to do with me or with the moon, but with the relation between me and the moon. The moon was very far away. Therefore, the angle under which I saw it changed very little when I was moving. Therefore, I had the impression that it was always with me. Whereas the trees were very close to me, and therefore the angle under which I saw them was going this way, and therefore I had the impression that they were going backwards. Therefore, I had the impression, I had the appearance of a moon following me, but it was not the case. There was so the whole explanation was clear to me as soon as I shifted from intrinsic properties to relations. I think this is something very important for science. Science as a whole, and especially physics, has done lots of progress when it was clear that one has to think in terms of relations rather than intrinsic properties. Let me give you an example. Now, not from my childhood, which is a little bit trivial.
This away from your mouth a little.
Sorry. Yes. Thank you.
Let's try that.
So,
No, that doesn't work.
yeah, I think it's okay. It's okay. Yeah.
Excuse me.
Thank you. So,
Yeah, that's good. That's
I
good.
think it's okay. So let's think about Copernicus and its astronomy. You know that there was an amazing change between the astronomy of ancient times, the astronomy of Ptolemy, that was such that the sun was rotating around the Earth, and all the other planets were rotating around the Earth. Now, in this framework, how can you understand the apparent motion of planets on the starry sky? You see here the motion of Mars on the starry sky between August 2007 and I think August or April 2008, so 1 year. And you see on top, you see the planet Mars, which is going forward towards the left, then going backwards towards the right, and then going forward again towards the left.
아, 사명마 두신 룸을
나
사명마 남주상 차도 저대고.
so the
그 떨어지고 수도.
so the Mars doesn't really make a full rotation.
Yes.
Okay, what you can
Exactly.
see.
I'm
Yeah.
speaking
이게
about
통다.
what we can see on the sky.
무슨
Namely,
통다지.
it's the appearance
아주
of Mars.
잠불린 대년 미기 야 때베나.
알았어요.
대단,
어디를
대단하지.
position, different position of world. That's right. Okay.
So now, to explain this strange phenomenon of Mars appearing to go sometimes forward, sometimes backward, sometimes forward again, Ptolemy invented an explanation which had to do with the intrinsic motion of Mars. So he ascribed to Mars an intrinsic motion which was made of two circles. Mars, according to him, was first rotating around the Earth by one circle, and then on that big circle around the Earth, there was what he called an epicycle, namely a little circle which was rotating also while Mars was rotating around the Earth. And therefore, as you see on the picture on the left, there were some loops. And these loops, when they are seen on the starry sky, appear this way, this strange going backwards and forward and backwards. So, according to Ptolemy, it was simple. You can explain that by a circle and an epicycle. Okay, but when he studied that a little bit further, he discovered that in order to account for the details of the motion of the apparent motion of Mars on the starry sky, he had to add not one epicycle, but a series of epicycles that had no end. So it was a problem. It was very artificial. Why 10 or 12 epicycles rather than 20? Nobody knew. So then came Copernicus in the 16th century, much later, maybe after 15 centuries. And he said, okay, let's suppose that in fact both the Earth and Mars rotate around the Sun. And suppose also that the Earth is rotating faster than Mars on its lower orbit, and Mars is going slower on its higher orbit. Then try to figure out what it is to be an astronomer on the Earth and look at Mars. And you will see that since Mars is going slowly, whereas the Earth is going quickly, we have the feeling that Mars is going backwards relative to us. And therefore, that explains why Mars looks like it is going backwards. It's not because intrinsically it is going backwards, but it's because the relation between us and Mars is such that we are seeing it as if it were going backwards. So here again, this is a very important move. Science made a momentous step forward as soon as it understood that certain explanations have to be given in terms of relations rather than in terms of absolute properties. Now, quantum mechanics. What is quantum mechanics? I would say it's a generalization of this idea. Namely, you know, in classical physics, only certain properties were supposed to be relative to the observer. Only, say, velocity and position. Nothing more. Mass was absolute, and other extension of bodies was absolute, and so on and so on. So only two types of properties were relative to the act of observation. Whereas in quantum mechanics, it's general. Any property whatsoever is relative to an act of observation. Spin is relative to an act of observation. Velocity, position, color of so-called color of particle, strangeness of particle, everything is relative to an act of observation. We say that all properties are replaced by or with observables. No longer properties, only observables, namely relational characteristics.
그래서 식지지도
돈으로 왔어요.
가
디 수진 처리야 랑원은 집에 캐주 유대는 마샤바
그리고?
캐주 되게들이야 다 캐주 다녀 마셔 통롱세지 통도로 왔어지 랍되게 그래서
나왔어요.
It's okay? Yeah. So, coming back to the wonderful saying of Richard Feynman that was quoted by John, he said, nobody understands quantum mechanics. Okay, and since Feynman was saying that, that was serious because he was the best American physicist ever and probably one of the best physicists in the world. So it was serious, but maybe he was wrong. I'm sorry. And maybe Bohr was right.
That's right. Bohr.
Maybe Bohr. Well, because Bohr said, it's true that all these things seem so awkward, but maybe in order to make them, to transform them into something less strange, we have to change our very concept of understanding. And the idea which was behind this idea of Bohr was that we have to change the idea of understanding the world into an idea of understanding our relation with the world. And this was exactly what Niels Bohr said afterwards, when he said, we are both onlookers and actors in the great drama of existence. We cannot subtract ourselves. We cannot describe the world as it is in itself independently on us. We have to understand that we are actors in the drama of the world. Werner Heisenberg also said that. He said quantum theory provides us not with an image of nature, but with an image of our relations with nature. As soon as you have understood that, and it's quite easy after all, many things in quantum mechanics become clear that were unclear before. So before that, I want to make a sort of pause at this point. Of course, you can complain. You can say, oh no, that's a regression. Classical physics was promising me a full picture of the world. And now quantum mechanics is no longer such a picture of the world. It's only a picture of my relation with the world, of our collective relation with the world. It looks like a regression. I want more. I want to go back to the good old time of quantum mechanics. And many physicists are like that. Even Einstein was like that, I must say. He said, no, I don't like quantum mechanics. It has so many strange features. I want to abandon it and to find a better theory which fits with the classical ideal. So obviously this standpoint cannot be dismissed easily because if Einstein had it, so it's a serious thing here again. Yet, if one accepts Bohr's and Heisenberg's point of view and try to go further in it, then something can change completely in our understanding. We can understand more. We can make many paradoxes, so-called paradoxes of quantum mechanics, clearer. And this is what I want to do now. Show you that if we accept that all the characteristics that are dealt with in quantum mechanics are in fact understood in terms of relation between us and the micro environment, then many apparent paradoxes are less paradoxical. First, example, the Schrödinger cat. I'm sure you know that very, very well. You have a picture of the Schrödinger cat experiment on the top right. The Schrödinger experiment is a box. Here you see also on the top, you see Schrödinger on the left and Bohr on the right, who are looking to the experiment. Now, the experiment is this one. You have a box, and inside the box, you have a big piece of radioactive material that has the probability 1/2 to disintegrate in 1 hour. Now, with the strange formalism of quantum mechanics, we say that during that hour, there is a superposition. In fact, the state of the piece of radioactive material is in a superposition between being disintegrated and not being disintegrated, just as what Arthur was explaining. Superposition. Both things are there at the same time.
근데
작배가는 여 쳐가지고 막도 차야강을
일단 디나로 때 감드나로 심지야 초지리야 두세단 거봐. 또 두세들이야 아니 간다 코란 두세가 누가 냐매 자장압주 담배 자장압주 담배 것도 자장압주 담배 두세들랑 근데 자장압주 담배야 두세들 많이 받지 내야게 누버여 받지 자장압주 담배 않고 또 제가 소리지 샤베나 다 두세디 누범 냠제 매바차 그래 두세도 누범 마냠바 내 데그레 세들이야 단단 게메라 봐 제가 납중납중 인도 갈라 다다는 콘텀도는 쉐베는 디 네갑랑 샤고 요레스 다 두세 디그 누바 냠베 네갑 지제 마냐바 네베 네갑 지제 다 냠바다 마냐바 니게 강롱그 네갑스다 강롱스라고 말하고 있다 니게 네갑 지금 네 먼저 제고 요레스 다 superposition set.
So in the same way as Arthur's photon, Arthur's photon was taking the two ways at the same time. Here, the radioactive material is, according to the description of quantum mechanics, I will come back to that later, what is the description in quantum mechanics. But at any rate, it describes in terms of a superposition, namely that it's both disintegrated and non-disintegrated during that hour. Okay, now let's go on. Then, if the atom, the piece of radioactive material disintegrates, then there is a counter that detects the disintegration. And suddenly it clicks. Then, when it clicks...
두 개씩도 하나.
Radioactive material.
두세라. 근데 간다 두스네 또 간다 녀랑 소리 봐.
radioactive.
So it disintegrates. One atom of the radioactive material disintegrates and sends a photon or an electron to the detector. And the detector, when it receives this photon or electron, it clicks. Pluck.
Yes.
And then it sends the signal that it has clicked to the computer, which is in the middle, which has these two eyes, you see. And then the computer has a hammer. It's a robot. It has a hammer, and if there is a signal that the radioactive material has clicked, it falls on the bottle and cracks the bottle. The bottle contains poison, and therefore, if the bottle is cracked, then the cat dies. Then a problem arises, the famous problem of Schrodinger's cat.
그래서
The Schrodinger's in Juba, a quantum physicist, Schrodinger's in Jure. The D means
No. Schrödinger is this man on the top left, you see. So Schrödinger's cat is here, and the problem is very serious because you remember that we have said that the radioactive material was in the superposition, half disintegrated, half non-disintegrated. Therefore, with this chain of events, the cat must be half dead and half alive, because if the radioactive material disintegrates, it's dead, and if it doesn't disintegrate, it remains alive. So apparently, and according to quantum mechanics, it should be half dead and half alive. But this sounds absurd, because when you open the box and see in the box, it's not the case. You see either a dead cat or a cat which is alive. So there is a paradox. What you could accept for an atom, you could hardly accept for a cat. What you could accept maybe that it was half disintegrated and half non-disintegrated, but how can you accept that a cat is half alive and half dead? There is a problem. This is the famous Schrodinger's cat paradox.
Can I just say, maybe we should add that there is no cruelty involved here, because this is a thought experiment.
Exactly. Yeah. Thank you, John. Yes, this is perfectly right. And I must say, I've personally gone to Schrodinger's house, and I've seen that, in fact, Schroddinger was no longer alive. His house was in Alpbach, that you know very well, because you have been in conferences in Alpbach.
Schrddinger.
In Austria. It is, his house is in
Oh, yes, so.
You remember that. And so I've seen in his house that he had many cats. And so he loved cats, in fact. So
Hopefully not experimented.
Yes, unfortunately it's a thought experiment, yes.
Experimenting on cats?
No, never. So now we have a terrible paradox. We have our hairs that are, you know, I don't even know the word in English. They are standing on our head. So what's the problem? But is there really a problem? Let's read the two sentences here. After Schrddinger preparation, the system atom plus cat is in a state of superposition. Namely, it's half alive and half dead. The state of the cat is half alive and half dead. On the other hand, there is another sentence here that says, one finds that the cat is either in the state alive or in the state dead. There seems to be a contradiction. One says that the state is half alive and half dead. The other says that it's either one or the other. Now, is there really a contradiction? I point out that without the word state, the two sentences would have no contradiction. If you understood this strange symbol as an expression of the information we have about the state of the cat, then there would be no contradiction. Because in one case, the information we have about the cat is incomplete. And in the other case, the information we have about the cat is more complete because we have opened the box and we have seen in it. And now we have a full information. So, the so-called quantum state expresses nothing of the cat, but it expresses a state of information which has to do with the relation between us and the cat. This way, you perfectly understand that there is no contradiction, because the relation between us and the cat has changed when we have opened the door of the box and seen it. The very difficult point, the only difficult point in this case, is that, as Arthur said, it's not only a matter of contingent ignorance. There is no one watching outside with a sort of bird's eye view who would say, oh, in reality the cat is dead, or in reality the cat is alive. There is no possibility to do that. What we have is no absolute property of anything, but only relations between us and things. So only relations. As soon as you have understood that, you can understand that there are two different types of relations. One of partial ignorance and one of complete knowledge.
맞아, 동업부 투별이야.
우서버 중에디면은
동업부를 투별이야. 아니 간다 미지게 통고요. 그래서 다 디자 단한테 관점 슈퍼포지션 제된 건 아주 통연다 통제 유니게 제외 버르고. 계절에서. 그래서 디 캐주얼
at least you see our world, our sun, 5 billions of years.
Yes.
So at that time, no observer.
Yes, absolutely right. Yes, but now, who is saying
But
that?
fact is fact.
Yeah. Now, Holiness, who is saying now that the sun it has 5 billion years? That's the point. Even that
that didn't show you, no? Some same shit.
science says that.
So in that case, we will have no criteria of distinguishing between what constitutes a true knowledge versus
Yes.
misknowing.
This is a very good objection, actually. Now, what is truth? Truth?
That's reality, Yamaroda.
네.
Distortion, reality.
Yeah.
So we cannot make a distinction either, to push that line of thinking.
Yeah. We can do that. Well, why? Because
Then I think it's no need education, no need research this work.
we need to be very educated observers. We need,
educated.
we need, for instance, when I say there is a glass, and Jimpa says, yes, there is a glass, and Chris says, oh, yes, there is a glass, and so on. There is a glass. Everybody agrees. This is intersubjective agreement.
Yeah.
It doesn't need that there is something like intrinsic existence of the glass. We just need to have, we just need to agree about our relation between us and the glass. If we agree, perfect, we have intersubjective truth. We have intersubjective knowledge. We have, everybody can do something and agree that it works. Physics is an amazingly efficient tool for getting effects that everybody can observe and that everybody can agree upon. We don't need any absolute standpoint. We don't need what in philosophy in the West we call the God's eye point of view. That's the point.
군주하고 대변하시겠어.
가.
군주하고 대변하시겠어. 참 통통해.
Now let's go on and push the logic of that. It may look strange, but it clarifies a lot. And then maybe we'll think about the philosophical consequences. Clarification 2, wave-corpuscle duality. Okay, it was very strange at the beginning of quantum mechanics to see that micro-objects...
wave.
지구들한테 아톰들. 지구들 뒤그라신다, 럽그라신다. corpus 럽도 수진. ontology 럽도 걸 들에 유추세르지네. 유제. 나 유추세르 봐. 유에다매 유메세 그 유추저로 봐. 유 간데스. 유추. ontology 럽도
It's about the word ontology, yes.
Yeah. How would you define it?
I mean, here it's wave-corpuscle duality without thinking that the wave property and the corpuscle property are intrinsic to micro-objects. Yeah. Ontology means the science of being, what there is.
Nature of existence.
The nature of things.
Existence.
But here we don't speak of the nature of micro-objects, but about appearances once again. So let me come back to the history of this wave corpuscle duality.
랑원의 예배 죄다 랑원의 예배 개죄 그게 되는 가서 중에 나의 중심으로 저다 참여미고 예배쟁이 봐. 르이도 저런 실셨으니 가다 수 이전 되고도.
So your line of thinking seems to be very much in tune with the Buddhist approach to all of these questions. For example, the very definition of what constitutes existence is something that is cognized by knowledge.
Absolutely.
And also what constitutes an object of existence, or it's sort of something that can be, something that is cognizable.
Yeah.
다음에 유디 참아도 돼 예배인데 유디 예배체 사마드 매버리니야 사마드 마지고 유드 매버케서 말다야.
But however, we do need to understand that that doesn't mean that the person who is looking at a particular glass, and if he turns his eyes away, the glass no longer exists. So we also need to find a way of avoiding that kind of consequence.
Of course, yes, of course. Well, yes, I don't want to go into such consequences, of course, but the problem is that, classical objects behave in such a way, in such a continuous and predictable way, that we have indeed the right to think that when we go out the room, the glass is still there. We have a right to do that because we know that it behaves in a very regular and predictable way. Whereas for micro-objects, it's not the case. They are behaving.
Yes, that's right. Yes.
They are not behaving in such a way that we can say that everything goes as if it was going on even when we do not observe it. Something very different occurs when we do not observe it. For instance, effects of superposition occur, whereas when we do observe it, superposition collapses. So something is very different between observation and non-observation. Now, let me come back to wave-corpuscle duality. You know that in the history of quantum mechanics, wave-corpuscle duality was discovered essentially by Einstein about photons. And when Einstein discovered that, he was extremely puzzled. He says, it's impossible. And yet, God seems to have found a trick. Because it's real. It's impossible, yet real. So God, who made everything, according to Judaism and Christianity, must have found a trick to stick these two very contradictory things together. Waves, which are extended, and corpuscle, which is a spot, a point, a dot. How is it possible that these two things are sticked on one another? How is it possible that a micro-object is both a wave and a corpuscle? Okay.
Corpuscles are particles.
가.
Particles are two in a 공부로와. The wave in a lapcha to the kuni moyo chane.
Corpuscle is a little body. Okay. But is it true that micro-objects are intrinsically waves and particles? The next steps of quantum mechanics have shown that it's not the case. In fact, if I had to say something in summary, I would say they are neither waves nor corpuscles. For instance, look at these effects on the left top. This is called a diffraction effect. This is the type of figure that is made by a set of electrons that are going through a little hole. And you see many circles. This is called a diffraction pattern, which is analogous to what we see on the bottom, which is an interference pattern. When we see an interference pattern like that, or a diffraction pattern, we say, oh, there is a wave, because usually waves do this type of pattern. But now, a wave gives diffraction and interference. But is it true, conversely, that any figure of any pattern of diffraction and interference means that there is a wave? Logically, it's untrue. A entails B, but B doesn't entail A. If A entails B, that doesn't mean that B entails A. This is one way. So, it would be true that diffraction and interference proves the existence of waves if there were no alternative explanation for the existence of diffraction and interference than waves. And it's not the case. There are alternative explanations. There are physicists who found alternative explanations showing how you can get interference patterns or diffraction patterns without waves. Well, I can show it to you, but it's a little bit complicated. Now, conversely, you see tracks in Wilson.
Michel, am I right in translating that if it's a wave, it will necessarily show these patterns?
Yes.
But it's not the other way around?
Yes.
Okay.
Exactly that, yes. So also, the same thing holds for the idea that micro-objects are little bodies. You see tracks on Wilson chambers or on bubble chambers or any type of device like that. You see tracks. In sun, you have tracks. And therefore, you get the impression that here there are little bodies moving ahead and leaving the track in the chamber. Now, is it true that this is a proof of there being little bodies? The answer is no. Why? Because it would be a proof of that if there were no alternative explanation of these tracks. But in fact, some scientists, especially Erwin Schrddinger, who wrote the celebrated Schrddinger equation and who formulated the paradox of the cat, Schrddinger found such an alternative explanation without corpuscles. He can explain tracks without supposing corpuscles. It's wonderful. So that means that none of this proof is a proof of there being either waves or particles. Okay. So now let's...
quantum theory ba mangbo chibu ka ngan the de tan Einstein ki nye bana shin ki we de kap ka she lab ka rig ta kap ka she du ka tuba ni ga yimbe mor bi chan du ka mun tan chin tin ge gu yo ra tan ge gu du ka da we de lab ka ta ni tan du ka ta ni ba ngun ji chebres ta ne yimbe tupchi de ka islam na ani tambe kenki lab ka number 2 adam ya kana dulge shu du chube shu ka number 2 ni ga yo ba yin zang din ani lab dan du ni ga da ni res she ge yo res ta ine shu di sha ba la che de yo ba la ji min ji du da ni yin go ba da ya lab ge shu sha ba shu da ba de tong gu de na yin ji min ji de lab ga da ni yin go ba ji kya ba chu ko go ma ba yin zang and this.
Now, if we have understood that, that means that we are left with no idea of what is there, out there, in the micro world. What is there? Are there particles or waves, or none of them? We don't know. Now, when we are completely puzzled, we have to go back what we have, what we know. What do we know? We know only one thing. There are phenomena. There are spots on screens. There are clicks on encounters. There are tracks in Wilson chambers, things like that. Just that, phenomena. And then, from this phenomena, we can exert reason. We can use inference. And there was a theorem that was formulated a few years ago by two French physicists called Jean-Louis Détouche and Paulette Détouche-Février, who showed only by dealing with phenomena, nothing about what is particles or waves or anything, just phenomena. And they said a theory applying to phenomena that are relative to measurement contexts predict wave-like distributions of these phenomena. So it's very simple. If you accept that these phenomena can only be relational, namely express the relation between our measurement apparatus and the micro world, then you automatically yield the consequence that the phenomena are wave-like distributed. So they have appearance of waves. Appearance only. That's the point.
Nezule duranche ödi. Nangzul benda tade.
Nezule tiniga kaya imeke jama shebche. 다 능주 코로나가 돈에 쉐바 잡제. 아니 랍 따부 나와다. 둘 따부 나왔어.
가.
둘 따부 나와다. 랍 따부로 나왔으네. 지금 능주 코레가네 쉐바잖아 모두 내줄 만두고 대비나 아니 개와튼 거였어.
So now we have the idea, very clear, which was already formulated by Bohr actually, that waves and corpuscles are nothing intrinsically existing or no intrinsic properties of micro-objects, but they are only relative to certain types of measurement apparatus we have. Certain apparatus will bring out wave-like effects, and certain apparatus will bring out particle-like effects.
내가 들으셨던 그 수진 다 기켜주 시고로 봐. 다 수진 기켜주 시는데 그걸 본다 단데 왜 그래? 어디 기켜주디 다 눌고 다니래. 랍고 다니래. 진짜 그런 랑원에 드베 캐주지 문제 제배는 강에 되고랬어. 때네 랍답으로 나왔다. 둘답으로 나왔어. 진짜 나wen 간 저에나 따디 있는 간주랑 간주다 그 제외니 버려요.
제 observe.
observe 돈에 아니 쉐바 잡두고 여러마도 그런 유랑 때네 예배 캐주지 문제 제배는 안 강에 되고랬어.
Now, let me go to another clarification. I hope it's clarifying, or maybe puzzling, but at any rate.
근데 뭐 그걸 가가시. 다마시 러브스럽네. 그런 거 거기 가다. 뒤처럼지 간 어디 걸었다.
나래.
다한테 뒤소리 좀 해주면 되고요. 가서 그게 캐시지가 캐주. 또 로이 뭐네 캐주 봉사죠. 어디 말로.
말해. 때는 뒤다부 자기요래. 뒤다부 자고를 가서 다
뒤안도 대형가가 매버서 주고. 대형가가 예배서 매버서 주고.
뒤찍으로 봐.
그래.
포톤기 다 쿠란기 랍게 다니래. 아니 수진 뒤게 다니래. 슬라민도 걸다디 캐주디.
아래 근데 그 뒤윤도 랍체. 먼저 주시는 코로코레 공부를 차 코로 제주를 차 거로.
때는 그저 땅뚜걸 포톤을 땅 거로. 단디 experiment 제백을 포톤 대비를 당겨 말을 당겨로.
그러다.
디강에 되고래. 그게
또 레지스를 통으로 곡계지무 열어.
나래.
곡계지기지로 되고. 그래서 뒤그 뒤인로 되고.
So what would rule out the possibility of explanation that
아도 뒤직슬로 있는 거라.
나래.
뒤두게 시행도.
나래. What would rule out the possibility of the following explanation that individual photons are corpuscular, and when you send them through the equipment, and then as a result of aggregation, it has this wave pattern.
Aggregation, that means many photons.
Many photons together.
I think
it is continuation.
Yeah, sort of,
one, because of that one proton. Photon, but it's continuation. The momentarily changing. The position change. So the very nature of that particle actually is changing.
The idea that it would be that the nature of the photon is changing.
The continuation is the
So the
continuation.
So couldn't one say that in a very discrete point in time, it may behave like a corpuscular, but if you take into account the continuum, it could behave like a wave. How would you rule that out?
Yes, it's a possibility. Actually, first of all, the collective effect cannot be involved just because the interference effect can be observed on one photon. It are completely isolated from anything. So first of all, it's not a collective effect.
Okay. But what about this idea of a single photon in its temporal continuum?
Namely changing sometimes as a corpuscle, sometimes as a wave. Yeah.
Yeah, but for example, it is moving.
Yeah.
So in a particular slice of time, it may be
so wave
corpuscular.
means is it like that movement?
Yes. Okay.
So and meantime, the particle itself also is momentarily changing.
Yes, I see.
Therefore, it is moving.
I see. I think there is only one model that fits your description and works quite well. It's the so-called Bohm, double solution or sorry. the hidden variable theory, the guiding wave theory. That's it. The guiding wave theory, which was formulated by De Broglie and by Bohm.
David Bohm.
David Bohm, exactly. Okay, so that he supposes that there is a particle which is guided by a field which has a wave-like property. And with that, he can explain a lot of things which are quite similar to quantum mechanics. Okay, so this is a model that fits a little bit what you say, and that works. That's a very important point, because when you propose an idea, you have to test it against all the facts that are predicted by quantum theory. And the only one theory which is a little bit similar to what you say and has already been tested against quantum theory is Bohm's guiding wave theory, on which you have one photon as if it were going. Oh, maybe I can show you the film more. No, I think it's too complicated. But at any rate, it's possible. But it's limited. It's limited to classical quantum mechanics, namely non-relativistic quantum mechanics. As soon as you go towards more complicated effects, such as quantum field theory, quantum chromodynamics, it no longer works. That's the reason why it tends to be abandoned. And why it's more, I think it gives a more coherent picture to assume, as I did, that there is no intrinsic properties or intrinsic nature, because this works throughout the whole spectrum of knowledge, of present-day knowledge, from ordinary quantum mechanics to quantum chromodynamics. So this is an argument. I don't say it's absolutely... This is
David Bohm the ma gyun robe kablia labrabo chek kan du yebuchi sheba jabyor dina quantum ki tonde ge chemang buji tonde de jab du yores de ine da ya telen de be nyok to sabe quantum ki namsha mang buji lian bom ge theory di nyok yo ma
I have a film also. So let me come to the fourth clarification, as I called it.
Yes.
For instance, you remember that Arthur has beautifully illustrated the idea that quantum particles are indistinguishable. And this is strange. How is it possible? The two bodies, solid bodies, that can penetrate into one another, disappear into one another, and suddenly reappear like that, as if they had lost their identity? It sounds strange once again. And you feel that there is something strange in the idea to ascribe such properties to solid bodies. Now, maybe there are no solid bodies, and this is the explanation. Schrddinger had exactly this idea. He said particles in the old naive sense do not exist. And modern physicists, such as Jos, the specialist of decoherence, said also exactly the same. Particles do not exist. This is the explanation of the difficulty of understanding this strange behavior of indistinguishability. Therefore, if they do not intrinsically exist, yet,
Mrs. James got back. 2003 said what?
You have spelled it in French, particules. You meant particles.
Yes.
Sorry.
French.
This is the French touch.
Oh, French English that's
Sorry.
Oh.
And so yeah, that's right.
It's always wondering whether that has a special significance in this context of talking about things and their attributes.
That's right, yeah. Oh. Now, it's true that, okay, let's accept that they do not exist. Is it true that they do not exist in the absolute? Okay, maybe they just do not exist in the absolute, yet they have some mode of existence because we can spot them. There are counters, so they have a mode of existence. Okay? Now, in quantum fields, what mode of existence do they have if they do not have absolute existence? According to two of my French professors, I had two professors in my studies, Jean-Marc Lévy-Leblond and Bernard D'Espagna, and both of them have come to the same conclusion independently. They said particles have the mode of existence of a rainbow, not of something solid, but of a rainbow. What is the mode of existence of a rainbow? It's a relational mode of existence. In order to produce a rainbow, you need three things. You need the sun, you need drops of water, and you need an observer. If there is no observer, there is no rainbow. There are photons everywhere, maybe, but not this wonderful circle if there is no observer or no photographic machine, actually, no camera. You need a camera or you need an observer in order to get a rainbow. You need the relation between three things. So particles are the same. And there is an illustration of that, a wonderful experimental illustration called the case of Rindler particles. Let's take a box in which you have pumped air, you have removed air, and it's almost empty. And you put a counter in it. It's empty of everything. It's empty of air, it's empty of photons, it's empty of anything. It's in the dark, nothing.
Can you take the photons out too, completely?
You can do that by cooling down everything, and therefore you remove energy, and when there is no energy emitted, no photons.
Yeah, but I mean, even the cool temperature has some property, material property.
Yeah, but you know, when you have a box without air, which is completely opaque to light, and which is at minus 273 degrees, which is absolute zero.
Cool itself, a phenomenon.
So, but the coldness itself is a
There
phenomenon.
must be some substance.
It's a phenomenon, but there is nobody there to touch it.
The classical physics knowledge. So it is a phenomena, the coolness. It has certain attributes.
So I think in modern scientific ways of thinking, cold is not something in itself. It is simply the absence of all heat. And so at this temperature of minus 273 degrees, as I understand it,
that's right.
there is no heat. So it's as cold as it can get. Doesn't mean there's some active thing there called coldness. There is a complete absence of heat.
It's absence of heat.
The degrees negative mega
Space.
So would you say that the space is also just an absence in the same kind of phenomenon?
Space is in a toxic channel.
So like kind of an absence of obstructive
It's absence of obstructive property.
Property.
Yes. It's, in some way you could say that, yes.
So 정무 써야지. 저 매매 channel.
So let's suppose that indeed, you know, you have cooled everything down. There is nothing, no air, no photon, and okay, the detector in the box confirms that. It says, I detect nothing, no click, nothing. Okay. So this is a phenomenon, absence of click.
선주제 영어로 되네 걸로. 저렇게 영어로. 정무 고라.
아니 두스레 저도 신이지 뇌제시 주셔 그때 주제시 주셔. So there is the
맞다. 그 사실 이건 시험을 지단 정식도 요르다.
나래.
배너 스페이스 나로 정식도 도.
라레.
어.
나스.
그 시처럼.
라레.
공부 가는 거 무슨 공부를 수.
라레.
어.
So let's forget about this experimental box. But even in the universe out there, there are
extreme coldness.
sites where there is extreme cold.
That's right, yeah.
So that's a real
It's a phenomenon.
That's a real phenomenon.
It's true, absolutely true. Absolutely true. And you detect
그 지용 들으시잖아요. 그 시담나디요 좀.
So if one can say that coldness, of that in the space is a phenomenon, why can't we say that the coldness in that particular box is a phenomenon?
In order to
개발가자 그래.
So what
슬로우도 coldness다.
Thank you for-
box난 coldness 개발가자.
So what is the difference? I mean, is there a categorical difference between the coldness that's out there and the one in the box?
Now let's accept that. Okay, there is cold in the universe, cold far away from the earth, far
Yes.
away from the sun.
Sun,
There is
that's right,
cold.
yes.
Indeed. Now how does it become a phenomenon? It becomes a phenomenon when you can measure, for instance, the velocity of a certain molecule, which is, there are some molecules, even in the vacuum, not many, only one molecule maybe in in a cubic meter. Then you take this molecule, measure its velocity, and see, how slow it is. This means that there is cold. This is a phenomenon. But if there is no molecule, it's more difficult. You have another criterion, however. The other criterion is absence of photons, or just photons with such a long wavelengths that they are very, very little energy and are almost like no photon at all. So here it's a phenomenon also. You see very low energy light, or almost no light, detectors that detect nothing, and you say, this means that it's very cold. So the absence of velocity of a molecule and the absence of energy of a photon means that it's a phenomenon of cold. Absence of. But this is a phenomenon because the detector says, I detect nothing. This is also a way of saying that.
무부제 이는 가베찬의 샤군이지. 가져가베찬은.
저자가 나 디샤우 그러다. 빅방 어중 공리야. 빅방 어중 공리야. 되게 계속 다지 하러다.
단도 구두 위험하다 단데 니메로.
가.
저거 권수는 시에베나.
빅방 어중 거지 하러 그냥.
라레.
다. 뒤도 배지 쳐봐잖아. nothing으로.
라레.
Space.
라레.
nothing.
라레.
No source of heat.
라레.
No source of heat.
So cold.
So cold, but it's cold as an experience. I mean, you're trying to get to the phenomenon of cold.
So this is
His Holiness's point is that before the Big Bang, there is no energy. So the absence of heat is there. The absence
but
of
Big
energy.
Bang obvious now.
The absence of heat is there, okay.
So I think here is 가사지고 1973 at CERN. So one Italian scientist. See, he told me about the quarks, quark number one. I still remember his face very clearly. You see, his two eyes
Piercing.
on my eye. And he mentioned how long the Big Bang happened. He says, exactly 12 billions of years. Then later, in Bombay, in India, one big sort of scientist sort of meeting. I just merely sort of invited there. So one American, the scientist, or certainly will be very well-known scientist, he mentioned since Big Bang happened, 25 billions of years. So big differences. Now, which is true?
12.7, I think, is the latest estimate. Is it 13?
We're not quite sure
We're
the
not quite
exact
sure.
date.
Oh.
단대절 13.
So then better is, I think, around, and then later so someone told me about 15 billions of years
15 billion. Yeah.
between there, 12 and 25. So in any way,
It's in that range.
I mean, that's true. Big
Yes.
Bang takes place. It is true.
That's what we
So
currently
before
believe.
that, see,
before that
we are not talking about investigating or thinking. The beginningless doesn't matter. You say, at least because of the Big Bang actually take place. Now before that, because of that, theoretically speaking, nothingness. So no source of heat. So coal must be there. Then such sort of state, the Big Bang, how take place?
Well, the
Now, from nothingness, Big Bang,
from nothingness.
impossible. So there is some kind of source or
There
material
is a
or
source,
particles
yes.
which creates tremendous energy.
Yes.
So there must be something.
That's called the quantum vacuum,
So-
Your Holiness.
Yes.
Coal,
Okay.
but something there.
Okay.
Yes.
This is what I wanted to say after. Actually, you know, let's go on with this box
Oh.
because it's
Come on, what's with this box?
보스 못하는 시죠.
because the box is easier than the universe. It's smaller. I can control it, have it here, whereas the universe is too big for me. So now let's consider this box again. You have an empty box. Cool down so that the detector detects nothing. Okay. Now you accelerate the detector.
게을게 지수이다. 디텍터 코레 새 예전이 디텍터를 맞더라. 디텍터를 맞다. 말이 가서 다들 새 샤야 코라. 그다 새 예지 코라. 코라 샤지 코는 예전이 간 두고를 맞도 그 탐지셔서 말.
Yeah, but the detector is for a very specific thing to detect.
Yes, you can
Not
add
everything.
You can add many detectors. A detector specific for molecules, for photons, for everything, and none of them detects anything. It exists. It's an experiment. It's possible. Now, let's suppose that we accelerate the detectors. We accelerate them. We push them, and suddenly, they click a lot. And suddenly they have detected something in what was believed to be the vacuum. Wow, that means that that was not the vacuum? That means, in fact, that this apparent vacuum was a potentiality of detection relative to a certain state of the detector. So it's not true that it's not true that there is nothing. It's true that there is a potentiality of detection relative to a certain detector.
No, very good. 되게 absolutely 요 말을 쓰기 그냥 absolute 식도 와요.
But I mean, earlier you talked about, how there is no such thing as absolute existence, but now you're beginning to talk about absolute existence.
Now this is very good, more balanced,
So
more
it's-
relative.
Relative.
Yes.
It's called the quantum vacuum. That's it. But it's here again. You should not. One should not think in terms of something absolutely existing. One should think of the possibility of relating it with something else. Because if not, nothing happens. You have to have some relation. You have to have some dependent arising, so to speak. If not, it doesn't work. It's not something which is there and it's waiting for. It's waiting for something. It's waiting for activation, as we say. Okay, now I wonder whether I have time still
How much
left.
more do you want?
I think I will. It
maybe
depends on the discussion, actually.
One more thing, perhaps.
There is one more idea in 2 slides, actually.
Okay.
Yes.
Okay, I think I have to clarify something also for you, because I know that you have been puzzled by this idea of quantum indeterminism, the idea that events have no cause. Is it true that events have no cause, even in quantum mechanics? I think
Could you maybe?
No, then the random stage.
Random order.
so. First of all, I will try to.
나로지나야 라괴 좀 멤버도 유대는 패지지 말해.
Some was saying that the idea that there is no cause at all is a tough one. You know, one could say there is no observable or observed evident causes.
안다 만주 우습지야.
So,
만주.
so, the-
만주 로트니직 우습지야.
so maybe there are no causes that we can observe by our means of our ordinary cognitive capacity.
Absolutely true. Yes, and I will concur with you, actually. I will show you that we can accept your idea even from the point of view of the best science we know. So let me first understand how this idea that there are no causes came out in the history. It came out from this kind of experiment. You have an electron, which is sent by some sort of gun of electrons, and then you have a bulb of light. And you want to know the position of the electron. In order to know the position of the electron, you have to send a photon on it. When the photon bumps into the electron, you catch it into a microscope, and then you know what is the position of the photon, and by inference, you know what is the position of the electron. Okay. Now, everybody knows also that when you do that, namely when you send a photon onto an electron, it bumps into it and disturbs the trajectory. Therefore, you wanted to know everything about the trajectory of the electron, but you have disturbed it, and therefore the next photon will catch the electron somewhere completely unpredictable. You don't know where, because the first photon has bumped into it and put it somewhere where you don't know. So there is disturbance. And therefore, you cannot reconstitute the trajectory of the electron point after point. Now, the tricky problem is that this disturbance is uncontrollable. Nobody can know what disturbance was imposed. And therefore, there is no way to reconstitute the trajectory, even by calculation, which we can do in classical mechanics. There are now two possible consequences of that. The second one, I start with the second one because it's more relevant. It's absence of causality. Now, now, how Heisenberg came to the idea that causality was no longer applicable to quantum mechanics? He said, causality is the ability to deduce the position of a particle when you know the position of the same particle 1 instant before. Then, the position of the particle 1 instant before is the cause of the position of the particle 1 instant after. Now, if you don't know the position of the particle 1 instant before, because of this problem of disturbance, then you run into trouble. You have problem, because that means that you cannot apply the principle of causality by lack of knowledge of what is present at the beginning. So it's not the case that there is no causality. It's the case that you cannot apply the principle of causality due to lack of knowledge at the beginning. This is what Heisenberg said. So this is a first point which is very important, I think. It's not true that you have to dismiss completely the idea that events have cause, but only the idea that you can apply the principle of causality for predicting, for the sake of predicting. Now, the second point was made by Bohr. The second point, which is in fact the first point on my slide. Indivisibility of quantum phenomena. What does it mean? It means the following thing. When you observe an electron with a photon, the photon is bumping onto the electron, you are trying to imagine that the electron has a trajectory, but that the photon has disturbed it. The photon has disturbed the trajectory. Bohr said, we have no way to know that the electron has a trajectory in between two observations. No way. Maybe it has not. The only thing that we know are phenomena. We catch photons in our microscope and say, this is where the electrons was. But what did it do in between two observations? Nobody knows. And maybe there is no sense to ask the question. This is Bohr's idea. And therefore, instead of saying that a photon has disturbed an electron, we should say that it's impossible to disentangle the object from the act of observation. And therefore, he said, the act of observation is a whole, an indivisible whole, a relation that cannot be dissociated into two parts, the part of the intrinsic properties of the object and the part of the intrinsic properties of the apparatus. A single whole, which is a relation, a dependent co-arising of a phenomenon from an interaction. Therefore, then I come to my conclusion. There is, well, I skip Karl Popper because it's a little bit complicated, but there is a theorem here, a new theorem, that shows that when a theory applies to phenomena that are relative to experimental context, then indeterminism arises. What does it mean? Does it mean, once again, that there are no causes? No. That means that they have no absolute intrinsic cause. But as Grete Hermann, a German philosopher who was a friend of Werner Heisenberg, said, in microphysics, causes are relative to the observation of this very event. So it's not true that there are no causes. In fact, there are only no absolute causes, no intrinsically existing causes, but there are causes that are relative to the very act of observing the phenomenon. So, phenomena are not uncaused. They are caused by a whole set of factors that include the measurement apparatus that triggers the phenomenon. This is my conclusion.
Wonderful.
Thank you.
So, instinct Darsha. Object sign, objectivity, instincts, diamaris. Kada Patanya dogji, Dashish, Tadu Zayona. In a DMH, those dog the Yevich, Diman map DMH.
So,
Chidunji Yevich. Ready go Chidunji, Mokaras, Papa Pazaka, you made a shot.
So this is, very much in tune with the way in which Buddhist philosophy understands. As you search further and further, the middle way philosophy, the Madhyamaka, as we search, say, for example, in objective external reality, which is a shared phenomenon, observed intersubjective. But if we are going to try to look for the essence by virtue of which it exists, then you get into this problem. So the existence at the ultimate level can only be understood in terms of these kind of relations. And in the Madhyamaka language, we say the existence of things can only be understood in relation to our conceptual imputation and the designation. Absolutely. And beyond that, to speak of an independent existence has no meaning. Right. But having said that, we also need to avoid the extreme consequence that, if you're not looking, then the thing does not exist. Or if someone doesn't label it, then the thing does not exist.
Yeah. I think, Your Holiness, this is the point that we're anxious to make, is that one of the dangers, I think, of physics is that people believe that there's a material universe which excludes all possible, say, spiritual endeavor, that the work that you do here has no basis in reality or fact, and that physics or the sciences somehow make it impossible to have a consistent philosophical position that would allow for a spiritual philosophy. But physics and the sciences, at least I think in Michel and my belief, are much more open, because the realities that we're working with in the sciences are phenomena. And those phenomena are always in relationship to an observer, to someone who's cognizing, imputing certain conceptual designations, and so forth. And that this is true even in the most detailed calculations and understandings of physics, the way Michel and I understand them, means that there's an openness, at least, to the pursuit of a spiritual philosophy. So the danger, which I think sometimes is perceived by those who do not know the intricacies, the intimacies of physics, is that physics must lead to materialism. And materialism rejects spiritual traditions. But science itself, I think both of us feel, and even physics, which is the most material science of all, do not lead to that conclusion. That's the reason these arguments, these very careful arguments, are so important for Michel and myself, is that what one shows is that the physics is a relational ontology, you could say, that what is real by virtue of a set of relationships, and that what one looks for absolutes, then they disappear. Right? But that does not mean that there isn't a way in which, relatively speaking, we inhabit a world, we function in that world, we can do science in that world, we can do theory, we can do experiments, we can have knowledge and so forth. But we have to be careful not to then project that which is true in that context into an absolute.
Theory? Relative, correct, relative.
ngogam prepare to sheba jabena ne seribu tama sheba sujen do ni ga tawa zengo ya janya ru jams mo ji ji ga de ra ma res ti kanta yo ma yo dan de ma den sin ti du du pu
这个光我的书上的还是有的ada just under spiritual philosophy says
no
the spiritual side is go yana mena
yes
시빈 대번이 남샤 시인의 샤인의 전에 다디 산제베 쳔네 다 디고 배주쳔이 봐 그러면 코로나인데 시인의 샤마도 스피리추얼로 투여나면서
so holiness, you know, it's very true, you know.
But the is loving, you know. Go by the spiritual living. The is loving, spiritual living sometimes.
So it's very true, you know, about the importance of being able to sort of think about this relational ontology, that the existence of things are understood in terms of their relations. His Holiness is taking up on your phrase spiritual philosophy. If you, for example, look at the Buddhist view and the Buddhist presentation, yes, if you look at the presentations of, say, for example, Four Noble Truths, then the last two truths, the path and the cessation, then they have a more...
I mean, last two truths.
Yeah, last two truths.
Two truths.
Then one can refer to them as belonging more to the spiritual domain. But if you bring the notion of the two truths, the conventional truth and the ultimate truth, the Buddhist presentation, then in some ways they are really secular. You know, they are not really spiritual in the sense of spiritual practice. They
Just
are really
just investigate what's the reality.
Investigation of reality.
Oh, Buddhist is it that understanding of that because of the reality apply or practice as a counter force of our distorted sort of emotions. So generally itself, I feel it's nothing to do with word of spirituality. That is my view. But I don't know.
Thank you very much.
Wonderful.
Thank you.
Thank you very much. Would this be a good place to pause, since we've come to a certain place in a long discussion, and then take up after a break?
Or would you like to have a little bit of question and back and forth?
Kama test to dan de samjo nangyu na yan totin kashi nangyu na samjo nangyu na yan
Another 15 minutes.
Yes, we can stop here.
Good.
Yeah.
Okay. So we stop for lunch now. Thank you very much, and we'll reconvene at 1 o'clock, I think.
1 o'clock, yeah.
Your Holiness, thank you.
Thank you very much.